I am recording. Hello Sabah, hello Joel, hello Mika, hello Ricky. So today we have PLD number 36. Yes, it is crazy. So we have two LeetCode. The first LeetCode is gonna be source colors, and the second one is word break. And today it's gonna be hosted by Sabah. Let's go! I am ready. I'm excited.
Hey everyone. So today as Mons have said, we're gonna work on two lead codes, sort colors and word break. We can start with sort colors. Okay, so the problem says, given an array of nums with n object, colored red, white, or blue, sort them in place, so that means in the same array, so that objects of the same color are adjacent with the colors in the order red, white, and blue. We will use the integers 0, 1, and 2 to represent the colors red, white, and blue. So 0 for red, white for 1, and 2 for blue. You must solve this problem without using the library's sort function. Okay, what they meant was that we need to, let's see the examples. So they meant was that we have an array that consists of three numbers. So either zeros or ones or twos in whatever order, and we must order them so that zeros, which is red, are first, followed by ones, which are white, and then followed by two, which is blue. So basically we're sorting this array, knowing that this array only has three possible numbers, either 0 or 1 or 2. So in this case, we had 2, 0, 2, 1, 1, 0, and it became 0, and then 1, and then 2. Same here, we had 2, 0, 1, it became 0 and 2. So this is a pretty easy problem. It has many ways of solving, right? Let's take this.
So each color is a number?
Yes.
Mm.
So let's take it here.
Oh, I see.
So in this case, we have this, and this is the Dutch flag, but it's like sideways. I think the Dutch flag is
Is
red
that
on top.
it's close to France too? I think.
No,
France.
France is like flipped.
Oh,
The blue is on the left.
oh.
But Dutch is like they're horizontal. Yeah, red top, white, and then blue. Or flipped French, I guess. So in this case, we have, let's put them here so we can see them better. I have two blues, two reds, and then two whites. And then we are supposed to take this array and sort it without using the sort function. Basically, just sort it, right? Does anybody have any questions about the issue? If not,
Yeah, Omina,
then
please stop. That is disturbing.
does anybody have any idea on how we can start? I know at least two ways of solving this.
Okay, can you like read the problem one more time, please?
Okay, you can read it again. So given an array of nums with n objects, colored red, white, or blue, so 0, 1, and 2, sort them in place, so within the same array, so that the objects of the same color are adjacent, with the colors in the order red, white, and blue. We will use the integers 0 to represent red, 1 to represent white, and 2 to represent blue. We must solve this problem without using the library's sort function.
Hmm. I think Minatollah suggests something in the chat.
We will swap the value as we loop through the array. Okay, that's an idea.
Wait, can you
Um,
explain it? Is it like a two pointer?
Actually, it's 3 pointers, not even two. So we can have a pointer to the left, pointer to the right, and then a current pointer that keeps um, going through the array and swapping them. So basically, if we have a pointer on the right, we can, whenever we have, for example, a 2 on the right, we can move that pointer forward so that we don't even look at this side, right? So if we have the point, so this 2, we know that the last element is in the correct order. And it's the same for the left pointer. If we have a 0 up front, we can move it to the next element, knowing that all the elements before it are like sorted.
Basically, just you loop through the array. If you find 2, you swap it with the right and decrease the right by 1. If you find 0, you swap it with the left value and you increase the value of the left by 1.
Exactly, yes. So you move the right one backward and you move the left one forward whenever you have the right value. So let's make a little bit of a simulation. So we have a left pointer that points to the element to the left, a right pointer points to the element to the right, and our current pointer that goes through the loop, the array. So basically, when we go through the array, the first element we're gonna check is a 2. Now we know 2 should be at the end, right? Because it should be 0, 1, 2. So 2 belongs at the end of the array. So we swap these two elements, right? Now we know that 2 is at the end of the array. We don't need to look at this element again because we know it's in the correct spot. So we move this pointer, the right pointer, forward, or I guess backwards. That means this is the end of our array that we can see because we know this element is already looked at, right? Now we look at this element again. Then it's a 0. It's in the correct placement, right? So we move the left forward and we move our current forward, right?
Oh.
And then again, 0 is in the correct placement. We move the L forward and the current forward. Now we know that this 2, it's in the correct position. It's not in the correct position. It should be at the end of the array. Now our end of the array is this because we know this is correct. So this is our right pointer pointing to the last element of the array that is not sorted. So we swap. Now we have 2 in its correct position. We move its pointer forward. Now to us, this is the end of the array because we know the elements, I guess, beyond it are sorted. We can do the same here, right? We know the elements before this are sorted, right? And the loop ends, I guess, when the current equals left. Yeah, and this is it's 1, so it's not 0, so we move it forward. Yeah, and our array is sorted.
Wow. Okay.
Is that clear enough?
Who have a question? Please don't be shy. Open mic or like write in the chat.
I have a question. I was wondering what is the purpose of the current pointer if we have the 2 already there?
Okay, I guess we can try it without this one. And we keep our left counter. We can try with that.
But if we count a 0 and we change our left pointer, we will have trouble. So we need the current pointer to move.
Can you repeat that, please?
Without the current pointer, how are we going to iterate through the array? Because we need the left to be 0 and the right to be 2. So we need them pointing where they are, not changing their value.
So example, say we have a lot of ones, right? We have one here, right? Once these two are sorted, only the current will keep going through these ones, because the left one, so say for, oh, what am I doing? The 2 will be at the end. The zeros will be up front. The left will not move past this 0, because technically the left only holds the zeros and the right only holds the 2. So this current basically holds the ones, and it keeps iterating through these ones.
Okay, I understand.
Okay, let's shuffle this and maybe we can see it in action. So the left is here, our current is here. So first we start with the 2. This is a 2. This belongs to the end of the, oh, let's put it this way, this is easier. So we start with a 1. This is a 1. This doesn't, it's not a 0, it's not a 1. So we put the current forward, right? This is a 2. 2 belongs to the end of the array, so we switch these two, right? Now this is in its correct position, so we move the right forward, and we move, this current stays here. Now this is a 2 again, it belongs to the end of our array, so we switch it with the 1, and we bring the right forward. See how the left and the current are not the same. Now the current is a 0. 0 belongs to the beginning of the array, so it switches with this. Now we know that this is in its correct position. We move it forward, and the count moves forward. This is a 0, so it switches with the left pointer, and the left moves forward. The current moves forward, and this is a 1. We don't do anything with the 1, and now C is equal to R, and I guess the loop ends.
That's crazy. It's a really good algorithm. Who have
it's called the Dutch flag algorithm.
Yeah, I just heard about it. That's amazing.
Yeah.
Who have
is it
question?
Clear?
Please don't be shy. Open mic and talk, or write in the chat.
Yeah, the left is only concerned with the zeros, the right is only concerned with the 2. Yeah, correct.
For me, I think it's clear. So left is holding zeros, and right is holding 2, and wherever is inside, either we're gonna push it to the before left or after right. If it was 0 and 2.
Exactly. So we initialize our pointers. L is at the beginning, C is at the beginning also, and R is at the end. So let's just write end for now. Now we start our loop, right? And this loop is only gonna check if it's a 0 or if it's a 2. So if current equals 0, then it belongs to the beginning of the array. But not just the beginning at where the left pointer is. Because to us, this is the beginning of the array, the first unsorted element, because anything before it is already sorted. So if the current equals 0, So if our current equals 0, then we swap with the L pointer, with the left pointer. Yeah. Okay, let's just write it. With our left pointer. Now, if current equals 2, then we swap with the right pointer. Swap with the right pointer. Now notice how we don't move forward when we swap with the right, because whatever we swap with can be like an element that is not supposed to be there. So if you swap, I guess, let's put this here, for example. I swap with a 2, right? And I put 0 here. You don't go forward because this could be not in its correct position. So you keep the count.
Oh, you want to check again?
Yes, you should loop again to check where we are. So we don't swap, we don't increment the current when we move right, but we increment it when we move left.
Yeah.
When we swap with the left.
So it's like we make sure before we move to the next one that element is not 0 and not 2.
Exactly. And then else, I guess, then we increment current. That means that we have a 1, basically. And if it's a 1, we just skip it because it's supposed to be in the middle. And in this way, we swap in the same array, and that means we don't change the array, we don't return a different array, because we're supposed to sort them in place.
Is it like the array they're gonna give us? It's only gonna have 0, 1, 2, or can we have another?
That's the thing. We will use integers 0, 1, 2.
Okay.
We know it only has 3 possibilities.
Okay.
Either 0 or 1 or 2.
Nice.
That's why we have the I guess the freedom of checking which number it is.
That's perfect.
Okay, is this clear?
Who have question, please don't be shy. Write in chat if you want repeat or like anything. All clear?
If it's clear, then we can translate this to code.
Okay, I guess let's do it.
Okay. So it says do not return anything, modify nums in place instead. Okay. Now we can name them left, current, and right. And right would be at the end of the array, so length -1. And we start the loop, so while the current does not equal or bigger than right, because the current will keep moving forward as long as it's below the right pointer. So while current smaller or equal than right, then if current, which is nums current equals 0, we swap with the left pointer. So we can do current left equals left current. So this way we swap these two elements, right? And increment current. So current plus equal 1. Okay, good so far?
Think it's good.
So now if nums current, and we're gonna do an elif here, if num current equals 2, then we only swap. Oh, and I forgot that we need to increment the left too. So whenever we swap with a pointer, we increment it. So if we swap with the left, with the right, we increment it backwards. When we swap with the left, we increment it forward. That means that whatever we swapped with is already sorted, we move to the next. And this is the spot that we're gonna swap with next time.
Wait, can you repeat that? Why are we gonna move
Okay.
both of them?
So say this is my array, right? And I am at current 0. Now this 0 is gonna get swapped with the left, right? Now this pointer should point to the next element of the array because this is already sorted. Like I said earlier, this part of the array, this whole part of the array is already sorted. So this pointer points to the next element that we can swap with. Now if I have another 0 here, I should swap with this, not with this.
Okay, but I thought you said we're gonna move with the both of them, like left and right.
No, not at the same time. We increment or decrement with the one that we swapped with. So if I swapped with the right, I decrement the right. If I swapped with the left, I increment the left.
Okay, clear. Clear.
So in this case, we will also increment left. And here, after we swap with the right, we will decrement the right.
And we're not gonna move current.
Current, no. We not move it because this new element needs to be checked as well. So,
because we don't know what did we move. Can we like check it in the same loop, or we have to loop again? I think we have to loop again.
We should be, yeah.
Okay, perfect.
It is better that we loop again.
Yeah.
So we decrement right, and else we increment the current. Okay. That looks good, I think. Yes. And if we submit it, it's 86. Now, there is another way to do this that doesn't include this swapping.
Oh, wait.
And this method can
86. Yeah. Nice.
Now, this other method basically consists of counting the amount of zeros and ones. So, for example, it doesn't use any pointers. So we go through the array, right? We count how many zeros we have, how many twos we have, how many ones we have, and then we modify the array based on that. So either have variables that hold the count, or maybe even a dictionary that holds the count, and then
just generate a new array?
No, you modify it in itself.
So I still don't see
one way. Okay, so one way I did it first is you pop each element as you add it to the count. So I have 1, 2, it's popped from this array. And then I have a 1, I have another one. This is so 2 ones, 1, 2, and you keep popping as you go until you have no element left. Okay, I'll remove some of these. Until you have no element left in your array, until your array is empty, but it's still the same array, right? Now you take this new array and you put them in order. You know that 0 should be one first, so you put it second, and then you go to the ones. I know I have 3 ones, so I will put 3 ones. Yeah.
Okay.
So this basically pops the entire array first, and then reconstitutes it.
I thought of
There is
idea is
another one.
like
Yes.
count the number of zeros, number of one, number of two, then just create kind of generate a new array.
You cannot generate a new array.
Oh, in place.
Yeah, in place.
Okay.
So you don't even return anything.
Yeah.
So even if you make that new array, it will not be counted.
Yeah, makes sense.
Yeah, do not return anything. But the idea is good, and we can go through this array in itself and override these values.
Oh, I see. Yeah.
So for example, let's just write here.
It's kind of the same as the idea that you shared before.
They're the same
popping.
concept,
Yeah.
just how you do it. So for example, I say zeros equals count, or nums dot count 0, and then ones, or nums dot count 1, twos equal nums dot count 2. And then you have, I guess,
Loop.
3 while loops. So
no, why? No.
Not even while, yeah.
Maybe one loop, and it's just checking the index. If the index is far from the range of the count, we're gonna put 0. If it is, so for example, we have 2 0. That means I'm gonna keep putting 0 until I get to index 2. So from index 2, I'm gonna keep adding 1. When I get index 3, I'm gonna keep adding 2. You know what I mean?
So for E in nums, no, in len, range len, nums.
And like now I'm gonna go to index 0. So like I need to put 0. So like check the index if 0 less than 0. If E less than 0.
Less than 0?
So 0 gonna have number 2 in this case of this example, right?
Zeros.
Only zeros. You put if I less than 1, you put 1. If I less than 2, you put 2.
So nums E
like that.
equals 0. Yes.
They will never, yeah.
Yeah, else if E is less than 1s, then put 1s. Wait, I think less than 2 there, wait. Yeah, less than 2. The else if second one should be less than 2s.
It will be else.
We can do even, yeah, so...
No need for anything.
So, because we have should be less than 2s, because like this it's not gonna put 1. So it's like saying, so if you can put if you can put your mouse on number 1 in the example, yes, that. So like, can you write indexes of them, like?
This should be 2.
One. It's okay. 1 0. Zero. It's okay. I think it's enough.
Okay.
So for example, I'm going E0. It's gonna be, is E less than 0? Yes, 0 is less than 0. Can we like put
so zeros
count?
Would be, okay.
Like
zeros would be
2.
Ones would be
3.
3.
And 2 gonna be 2. So so we need somehow to add index or something, right? Yeah, that now it makes sense. So if E less than 0, in our case is 0 2, so it's gonna be the index 0, we're gonna put 0, the index 1, we're gonna put 0 because 1 is less than 2. And now we're not gonna loop to the 1, the third element that have index 2. is gonna be if E, which means 2, if 2 is less than 0 plus 1. 0 plus 1, what is it? We can even do like if E greater than 0. This also can work. If E,
Greater than 0?
yeah, if E greater than 0 in LF. In LF, if we
This
did
one?
like, yeah, greater than 0. Zeros.
But
Yeah, remove
it
the
will
ones.
include both these two. You know? It will include both this and this.
Yeah, then we'll need another check or like yeah, I think before this is better. The 0 plus ones better.
Let's check it. Let's see.
Wait, we didn't finish simulation. Let's see if it's
No,
gonna
that's
work.
it.
So
Oh,
if
okay.
so, like 2, when you're gonna get to number index 2, it's gonna be 2 less than 0 plus 1, which is 2 plus 3, 5. Yes, it's gonna put 1. Gonna loop again.
And this
I'm gonna put 1. It's gonna reach there for 5, and then it's gonna keep it put into, yeah. It just makes sense.
Okay. Let's try it.
But I think the Dutch flag algorithm is faster.
I'm actually not sure.
Yeah, I think because this one have a lot of F.
Ifs are faster, believe it or not.
Really?
Not faster.
Yeah, I mean they made specific. Oh wow, that's crazy.
Okay.
Nice.
Like ifs are usually faster than whatever max or yeah, they're faster.
Wow.
Okay. Any questions before we move on to the next one?
I think it's perfect. Nice, good job. You explained it really well. Anyone have any question? If not, we can move up to second one.
Yeah. Okay. The second one is word
Word
break.
break. What is that? What is that?
Okay. So given a string S and a dictionary of strings word dict, return true if S can be segmented into a space-separated sequence of one or more dictionary words. Note that the same word in the dictionary may be reused multiple times in the segmentation. Let's take this here. I will separate these so I can explain it better. And actually even these. Okay, so we have two elements in this word dict, right? And we have our string LeetCode. Now it says that this dictionary of strings, or these array of strings, can be like, we can have multiple combinations of them, and we need to return whether or not any of these combination can return us this string. So for example, if we put leet and we put code next to each other, it would give us this string. In this case, we will return true because these two words, if put together in any combination, in any number of times, would give us this string. So in this case, it would be true. For example, if I say co and then another one would be de, this would also be true because in this combination, we can put them together and they would give us this string. If, for example, we had just this cannot be true in any way, because no matter how many times you put them together, no matter how the combination is, it will never give us this string. Okay? So, for example, again, we have apple, pineapple, right? And we have two elements, right? We have apple and we have pen. Now we know that apple, pen, and we said that we can duplicate this as many times as possible or as necessary. So that means that apple can appear twice to give us the same sentence. So in this case, we can also return true, because this reconstitution would give us the same string. Does that make sense?
But from where are we gonna get string? Is it like they give us array?
They're both given to us, yeah. So given a string S and the dictionary words.
Okay, so it's
So
an array
we
of
get
string.
both of them. Yeah. So S is a string and word dict is an array of strings.
Cats,
in this case,
and
cats and dog. We have cats, but we don't have this string, and there's nothing in here that can make up this string. We also have dog, but we don't have anything that we can put this combination of words. No matter how we rearrange them, no matter how many we duplicate, we will not be able to get this combination. We have cats, we have dog, we don't have and, we have sand, but we don't have cat and og, right? So we cannot over-align them. So dog and sand cannot be together because they both have D in them. So they need to be separate. So in this case, we return false because no matter the combination, it will never give us this string.
Wow, interesting.
Yeah.
Maybe recursion, maybe dynamic programming.
We know that the elements of the array are unique, so we don't have duplicate words, and only lowercase English letters. Okay, any questions?
It's clear for me, I believe. Anyone have a question? Please don't be shy. Do not be shy, we are learning. Do not let imposter syndrome take over your mind.
Okay, so if no question, then does anybody have any idea on how we can start? So say, for example, we have two word dictionaries or dictionary words, and we have this string. How would we go about finding if these can fit in here or not? Any ideas?
Let's think. Maybe recursion, we loop on the string S, but so we loop on string S, or no, we loop on each element in the word dict, and we keep, so if we have four elements, we launch a recursion function on each string that will go no, it's not gonna work like that.
No, keep going.
Okay,
You're
so
on the right track.
Really? Okay, so what I thought is we're gonna launch a recursion function on each string, and it's gonna go to the the goal string that we're looking for, and check it's gonna return if it's found itself there or not.
So in any position in the string?
Let me see. So it should be from any position, and like each part of string maybe we keep track of, and then if we have leftover, which mean none of the word inside did complete the check. So for example, if I have apple, okay, so here we have apple, pineapple. Let's say I have up, pineapple in my word dict, right? Up, pineapple, and I'm gonna go to up and go to the string and see a, p, p. Okay, I'm gonna return true or like something, wherever. The goal is like this function gonna mark the up. So can you do like a pin, select pin, color green for example, and just put an underline under up. So the first function did find, for example, up. So we have this word, and then we go to apple. We go to apple. Oh, sorry, not apple. Up. Wait, can you like change the word text to up and apple?
Up and apple.
Up and pineapple. Sorry.
And the pineapple. So
Up and pineapple. So my word text dictionary have two words, up and pineapple. So I did go to up. I did find it in the string. I did kinda somehow mark it. Now I go to the second word, and I go to the string looping first character p, l, no it not, and then I found p, and then I said okay, I'm right track. Pineapple. So put like another green line, and now I'm gonna check after I finish all the word dictionary. I'm gonna check if there is leftover, and yes, I can see that there is two character left over there. So I understand that I can't do this. I don't know, like this is just initial idea, but I'm sure there's some edge case that this will not work.
okay, that's pretty nice idea, I think. But for me, I think we might have to concentrate on the string itself. That will help us track where we end easily while we are comparing. So if we take the app, like we concentrate on the string, take the string and go AAP, then we put a kind of mark there. So when we come again, we are going to find a word in the dictionary that can complete from the beginning. If we cannot find any word that can complete from where we left, that cannot complete from L, then we know that there's no way we'll be able to find a word that can complete that string.
Okay, so you're telling me that we go from the beginning of the string, and when we found this word, we save it somewhere, right?
Yeah.
Uh-huh.
We can just put a pointer at where we left it. That's if we are using a loop.
Okay, say this is our pointer.
Yeah.
Now we're at L. What do we do now?
So we're going to go back again and check all the words inside the dictionary. If there's anyone that can start from L, anyone that can complete, that can just start from L.
So we compare letter by letter.
That's pretty much what we might have to do. And I'm just thinking.
How about we compare word per word? So instead of going through the string, we go through this and we check, is this at the beginning? And we compare the entire word, since we already have the word, instead of comparing one letter at a time, right? And once we find this word, then we move on to the next. We say, okay, this is gonna return true. We already have this word. We move on to what's after it, and then we start comparing again. Do we have LE or anything that, or any of our words is after what we had? So after app, this LE, does anything resembles that? If not, then we return false. If, for example, we had LE, then we would say that the first word exists, and our pointer would be here. And then when we would be comparing again, we would find this. Again, this equals this. Does that make sense? I think that makes more sense than comparing letter by letter.
That makes sense. If we can put a pointer at where we stop and we are able to cut that and compare with a particular word, that will make sense.
I think it's not going to pass for an edge case. Say, for instance, you have a list that has the words up, LE, and pen. So remember that they said we can repeat a word, right? So if up works for the first 3 letters, you're going to come across up again after pen. So that means if you check up first, but maybe you have to check it again if it reoccurs so you can use it again.
Yes, that is correct. And we can use it again. Since we're going to start our search from the beginning.
Yes, from next time we come to check it, we'll use all the words that are in the dictionary again.
I didn't catch that. Can you
Sorry,
repeat,
I mean the edge case will be handled since whenever we come to check from where we left it, like when we check from the pointer, we will be using all the words inside the dictionary. So we will, if we have to reuse a word, we will have to reuse it.
Exactly, true. So in this case, since we are app, we have our app here. Now when we move forward, we're not going to check from LE. We're going to check back from app. We're going to check if app is here. No, it is not. If LE is here, then yes, it is. And then we will put LE, and then we skip to the next. And we're not going to check from pen. We're going to check from app again. Is app here? No, it is not. Is LE here? No, it is not. Is pen here? Yes, it is. Then we put it, and then again. Starts with app, and then LE. Make sense?
I think it does. Do we go for it? While you were guys discussing this idea come to my mind, but I don't know if it's gonna work. Let's just suggest it. Let's see if how it is. Like, what if we just remove the words from the original string? So let's say we have a word.
Good idea.
We have like a dictionary word. So we sort the dictionary to start from the big words. So let's say we have up and pineapple. So I'm gonna sort it, so pineapple gonna be the first one. And then I'm gonna go to the original string. I'm just gonna like maybe transfer or like just remove pineapple from that string. So wherever there is pineapple there, it's gonna be removed. But when I remove it, I'm gonna replace it with like maybe underscore or like star. You know, so just other string, other character doesn't connect with each other and create a new word. You know what I mean? So for example, if apple, pineapple word, and I'm looping to up. Can you turn up to a star? Like 3 stars? 3 start, like, or I think it doesn't matter. Yeah, 1 start is enough. And then I'm gonna loop to pineapple. Then I go to origin string and just remove pineapple. It's gonna become a start. So wherever I find words that are in word dictionary, I'm gonna turn on the start, and then check if the last S, if it all start or it have some characters. What do you think? I'm not sure. I didn't go in
try that.
details, but it's my work, but I don't think it will.
So you say
Yeah, it's
we
pretty good because
go
it might
through.
help us handle a situation I was thinking. Because at some point we might be using a word at first, then that word doesn't complete, doesn't help us get the answer. But if we had used other combination, we would have gotten to an answer if we had. So I think that case, this algorithm might help us handle that.
Yeah, I think it works even if there is a need to repeat. That means you'll be having more.
So like this.
So sort word text. I'm not sure if the sorts will matter, but I think if we remove small word before big word, we're gonna find problems, because let's say I have up and apple. If I remove up first, when I'm gonna go check apple, I'm gonna find out that apple doesn't exist, even it was before, because I removed the first part of it, right? So let's
So
say you
for
have
example,
apple,
like this.
and they have a word called, let's say apple phone, right? Like apple phone, and write like up, and in the word text you have up, and you have apple, and you have phone. Now if I go to up and I remove it, turn it as a star, like, okay, I go to up, I remove it from string, it's gonna become star. Now I'm gonna go to apple, and I'm gonna say like I didn't find apple, but it was there, right? Know what you
Okay.
mean?
So I understood. So we sort in reverse,
But is it
right? So
matter?
biggest
I'm not sure.
we
Yeah, what if
try
the
that.
small words were behind?
So the big words should be the first one, or like sort the characters alphabetic. I'm not sure.
I guess by length makes more sense.
Okay,
We can try that.
and then we're gonna loop through
So
dictionary and replace all the word we found in string with start.
let's write some code for this. So word dict. There was this sorting thing. Don't remember. Sort or key or something.
Sorted.
Yeah, and key equals len. Reverse true. Right. Oh, but we have arrays, so I guess. And then we have sorted d with key equals len. Let's see if this one actually works. Okay. And then reverse equals true. Okay, see?
It work?
It
Okay,
sorts by length.
nice.
Okay.
Wow.
Okay. And then for word in word dict. We replace. There's a replace function.
Replace, yes. So like replace, you give it like the word that you want to replace. And what?
Let's try it. Then a dot place with asterisk. Okay, so that works too. And then we return true if what? So we loop again through this as our.
So I think we need to do word equal word replace. I don't think it replaces in place, or it does it. Not sure.
Oh, that's right. We
Like so, like word equal.
go by. We can go by like.
Wait, I think we can keep it like it was.
Range.
Just put a word equal.
But word will not. Okay. S here, not word. It's S. Yeah. Okay. Because we should not be changing the word. We're changing the original string. It's S that we're replacing.
Oh, yes.
Okay.
So yeah.
Does it change A? No, it does not. So we need to write S dot equal.
Yes. Okay, I see it now. And then we check if like S is equal.
I think we'll need to loop through S. So for
there is a short way. We do. So if you do check if S equal the start multiply by the length of the string.
Okay.
So like start this. Multiply by the length of string.
Okay.
Wait, is that correct?
Let's try it. Let me try. So we have 4. S equals start times len of S. Sure.
Yeah, because when you do string multiply by number, it generates that string a couple times.
Okay, I think that's.
But I don't think this is gonna work. If it solves 3 cases, I will be happy.
We can surely try.
No, it's not gonna work.
List object has no attribute. Replace.
You should not be modifying S.
Oh, word.
Yeah.
Okay. But there is gonna be edge cases. There is no way. Yeah. But how many is pass? It's pass 40. Okay, that's good. So impressive. six edge cases. Wow. Can we like see which one? EBC.
Okay. So we sorted this. So we're starting with ABC, then CD, then A, then B. This should work.
Wait, what the output? Maybe. Yeah, print is nice. Also, like print the string, how it become at the last. Is it like replace all of it?
It didn't Change. Oh, because there's no D. There's CD, but not D. See?
I don't follow.
So there is ABC that got censored, I guess. But there's no D alone. There's C and D. So it could be reconstituted with A, B, and C and D. But it started with ABC.
Oh, it's
right?
replace. So it's replace. Okay, wait. Can you do print in?
Let me see if removing the sorting does anything. Okay.
Wait.
So it started with the smaller element.
Yeah.
It just needs
So
to
it
be a
started
little
with
bit greedier. What if you start by putting the shortest words first?
Start that. This would also work.
But is that mean gonna we have new edge cases that doesn't work now?
Yes.
Wait, what was the edge case? The other one. It was A.
It passed. One passed.
Oh,
But
when we
this
change
one,
it.
so we have 4. 1, 2, 3, 4. Why not?
A. B, C.
I think we need a recursion here.
Yeah.
Because it did triple A.
Yeah,
and then
it beats both possibilities. In this
recursion.
case, it's not greedy. It's
Yeah. If I was good with backtracking, I would have said we should use backtracking here because we should try to complete the solution. If the solution doesn't work, we try another option continuously until we exhaust it.
Yeah. Either by
It looks
backtrack.
Thanks, Toby.
I don't think this algorithm here is gonna work for all cases. It's gonna have a loophole for sure. We can so this one did solve 33, the other one did solve 40. So maybe we improve the 41 because it have only 6 cases more.
I mean, there is the other way of doing it where you keep shaving off the first, but you keep comparing with the beginning of the line. But that is also like recursion.
Yeah,
so
I
I'm
like that
wondering
one.
if we can do recursion with this. So we replace, but we need to find a way to check if it actually replaced or not. And if it did replace, then we start from the beginning. If it did not, then we move forward. Okay, if word and s, then we replace, and then we this should work. We may need something. Let's try this first. Okay. Car. Oh, so it doesn't back.
Can you read description again of the task?
Given a string
yeah.
S. with dictionary of strings word dict. Return true if S can be segmented into a space-separated sequence of one or more dictionary words.
Okay, so there is no way we know where is the word start or its end. The string they give us, right? Yeah. I guess it's
So
recursion.
backtracking would have worked, I think.
Yeah, backtracking or like dynamic programming. But nothing come to my mind.
Can do it the way that I
How about
said.
we just
Yes.
Isn't this?
brute force?
Yeah, brute force will work. Definitely. Can do it. Can even... If we want brute force, how we gonna do it?
Let's go through them one by one.
Hash table?
Not necessarily. Okay, let's go back to the drawing board. We can, in this case, start with, for example, we go through this, and once we found apple, we remove it entirely, right? And then we move forward. That's, I think, better than doing this, maybe, because at the end we'll just have an empty array or a string, right? But since we're starting from the beginning, there's no way to link words, right? We are not going from the middle and removing this, right? We keep going from the beginning. So in this case, we look if we found LE. If not, we return false, right? And we go back to apple. In this case, again, we check for apple. If we find apple, we remove it, and then we keep going forward until either we're at the end of the dictionary or our string is empty.
Okay, one more time, please. My brain.
Okay. So we have a string S, right? And we have our word dict. We loop through our dictionary, comparing each word with the beginning of S. So,
like we because what if it wasn't in the beginning?
we go through the beginning. We keep only our pointer at the beginning.
Okay.
If we find it, we remove it. If we don't find it, then it's false. We completely disregard that combination.
So it's like we're gonna. So the word itself, it's gonna be in the middle of string.
Yes, but it's the beginning of the string so far. Because in this case we had apple.
Yes.
Right, but we removed it because we found it.
Okay, what if we have phone apple? Do we remove it too? Because it is in the...
We will remove phone. Yeah, we will remove phone. And then when checking again, we will start from the list apple. This won't work. And then...
Okay, but like, what if the word was phone apple? And then we are checking the word apple. We're gonna remove apple. So like, what if the word was, let's say now we are checking for phone. And the word, we start with phone. And the word is apple phone. We're gonna go to first character. Wait,
apple
why
phone.
remove it? So we're gonna go to A, it's not A, it's not B, it's not P, it's not L, it's not E, then we're gonna remove it? Or like, because I misunderstand.
So we go through our word dict, right?
Mhm.
We check with app. We have app. We remove app. And then we check again from the beginning, right?
Mhm.
Um, we find any word that starts with LE. We can't find it. So we remove this combination that starts with app. So technically backtracking. We go back to the beginning. Then we find apple. We have apple. We put apple, right? But we don't start from the beginning with apple. We go to the next dictionary word, right? So it's apple. Good. We remove apple. We go to phone, right? We put this again here and then we start. Is this apple? No, it is not. Is this apple? No, it is not. Is this phone? Yes, it is. Then we put it and we remove that.
Oh,
So now it goes.
wow. Okay, so we are actually looking for the first word. Because if the first word
Exactly.
doesn't exist, that means none of them gonna. It just mean our dictionary is not gonna work. Okay, I see. Wow.
So
Okay.
either we have a pointer or we just remove the actual word that we
Mm,
found.
okay.
Do this and then
So we start from the beginning, and for our case, we're looking. Okay, what is the word that match the first couple character? And we are like, okay, apple match it. Then we remove it. Then we go to the next word, right? Like this. So loop
yes,
to the word text.
yes. And then compare the word with the beginning of, so compare the word with beginning of S. Right. So if it is at the beginning, right, then we return true. If it is not, then we return false. But not only this, we're gonna have a recursive call because if I return true, it not only means that this is in its right place, but also that the rest of the word are in their correct places.
Wait,
So
can you
not
repeat that,
only
please?
should it be so not only should this word be at the beginning of the
Mm-hmm.
of the string, but the rest of them should too. So I will call this function again, right? With the next,
Parts of the
like,
word. What
with the
left?
rest.
Okay.
Yes.
So it's gonna keep looping in each word, and each time it's eating from it until either it's gonna be
Exactly.
empty, so we just find
Because
all the word, or
uh-huh,
the case where we have something left, right?
it returns false. Yeah, it returns false.
Wow,
So in
genius.
this case, I will either pass this pointer or I will pass the array without this. So I give it this again and I tell it, look through this, tell me if this is true or false. And I will only return true if you are true and I am true. That makes sense?
Okay,
So I am true means that I compared with the
please.
beginning, and
Mm.
you are true if the rest of the string is. So,
Mm.
yes? Somebody
Okay,
was talking.
please. Can you try something like so? In a case where you are talking about Apple phone, so in the dictionary we have Apple, but what we have. Okay, please complete.
Repeat.
Please complete the Apple phone again. Let's the Apple phone.
Hopeful? Oh, okay.
Okay,
Uh-huh.
so we have Apple, and we have LE phone, not just phone. We have LE phone, not phone. No, no, the LE
Phone.
joins with the yes.
Like this?
But we also have Apple. We also have Apple.
Apple. Okay.
Yeah, we also have Apple. So just try. Let's see if the algorithm would work in this case.
Okay. We start with L, with app, right? Do you want them in a different order? Because this will return true immediately.
No, what about order? Okay, okay. You are going to put app in between them. Put Apple in between them. Sorry, Apple in between
Apple
them.
in between them. Okay.
Yeah.
All right. So it will start with app. It will compare with app. It will find app. right? It will remove app. Then it will start again. Is this app? No, it is not. Is this Apple? No, it is not. Is this the phone? Yes, it is. I think
Okay.
you are better starting with Apple. That's where the issue would be.
Okay. So what about what about the algorithm where we had phone at the end? Okay, so you remove LE from the phone. How would that work if we have if we remove LE from the phone and we have Apple in between them?
So like this.
Yes, and we have Apple in between.
Apple in between.
Yes.
Let's see in the middle.
So it will
Okay.
start with app. It will find it. It will remove app, right?
Yeah.
So I think this is what backtracking is. So, and then it will go again. Is this app? No, it is not. Is this Apple? No, it is not. Is this phone? No, it is not. This combination that starts with app will return false. And then
Okay.
it will loop again, starting with the next word.
Mm.
So if this
Okay.
returns true, then it will immediately return true. If it
Okay.
returns anything but true, it will loop again. It won't start with app, it will start with Apple this time. So now
Yeah.
we have,
That's pretty much backtracking. That's backtracking.
so
Yeah.
now we have Apple, it will start with Apple, and then the rest is.
I have a question. Why
Mhm.
we not? So, for example, we have app, Apple, phone, and the first string we check was Apple Home. We found that exists in app, so we remove it. Apple, we found it, we remove it. Now, when we're gonna check what's the rest of the string, phone, like it's okay if we start from Apple, app, phone again, or right? Maybe if it was like, oh, okay, maybe it's away from the design of backtracking. But like, my question is like, it does not matter like if we check again same string with the 3 element. So we're gonna start again. Up, Apple phone. We found it again. Remove it. Then look. Okay, so it's probably a question of optimization. Like, if I did check this, there is no to check it. I don't know. I'm confused. Did you get my idea?
Okay. No, I did not.
Okay, so let's say I have Apple phone, right?
Uh-huh.
Right there. Now, the idea is like it's gonna be a loop that's gonna check Apple first. It's gonna find it, and then it's gonna remove it and send the phone string to the rest of the word dictionary, or same dictionary.
Yes.
Now this
No, with from the beginning. It will start again from the beginning.
starts again for. Okay,
Because
so
what
we're
if
not gonna
phone
change it.
was here?
Okay, so we're not gonna change the
Because
word
what if phone
dictionary.
was first? No, we won't. The phone dictionary is one. It will not change.
Okay, so we're gonna
But
the rest of string we're gonna still check it on all the dictionary again.
exactly, yes.
Okay, I see.
Because in this case, it will start with phone. Phone is not. App, we'll skip this one. And we go to Apple. It will find Apple, right?
Wait, why we
But
skip that one?
for phone, because it's gonna return false, and we're gonna try again, and we're gonna move to Apple. I'm just skipping to
Oh, okay,
go
okay,
to
okay.
straight to
Okay.
the point. So it's Apple, and then we find Apple, we remove Apple, we return phone. If I go from here, say app was here. If I go from here, there's no phone after, but I know there was phone before. So we must start from the beginning of the word dict again.
Okay. Okay, maybe
Because here I find Apple here, and you say we return just these. We disregard the first ones.
No, that's not what she said. I thought that's what she's doing.
Okay. No, that's not what I'm. We pass the word dict again, so it starts
Okay.
from the very beginning.
Okay, perfect.
But when it returns a false in one of them, we don't start again. We move on to the next one, because if we start again, we'll fall into the same word.
Okay, that's what I did.
So
I did not understand.
was
So if it
like
return
this,
false.
Yeah, if app returned false, I will not go again and check phone and then check app again. It will again return false, and I think it's
Oh, I see. Okay, now I see it.
infinite recursion. So I go to the next one, which is Apple.
Oh, now it makes sense. So I need to like stay pause in my place and check one of them until I find one, then I can continue, or I stop there everything.
Okay, so I think when you encounter, for example, you encounter Apple, then it returns true, and then you go and start again from the beginning. But if it returns false, you continue till the end. So when you get to the end of the dictionary and then it returns false, I think that is when you return false. Like you break from the loop entirely. I don't know if I'm clear.
We return false here. At the end of the loop, if no true were given, then it's automatically a false.
But we're still missing a condition inside, right? So
we compare the word and
we return true.
Yeah. Compare the word with the beginning of S and call the function with the rest of the so we remove this apple, right? Oh boy.
Okay, so we're gonna
remove this apple and we call it again with the rest. Either this or we send with it like a pointer.
Okay, so let's do this. Let's compare the word with beginning. If it is true, return this. If it is false, return this. Is that what we're doing?
If it is true, you return true. If it is false, then it keeps going through the loop. It doesn't break.
Okay.
Because it checks the next one.
Okay, wait. Compare the word with the beginning, and if it is true, let's say we compare it. We said like this. If this it is give true, then I need to call another function, recursion function, right?
Yes. On the rest of the string.
Okay.
So it should check this one too.
Okay, so maybe we write compare the word with beginning of s. If it's true, call recursion. Like not
and
end,
if that
right?
also is true, and would work too. It would be
oh
yes,
yes,
like
it's gonna be true and false.
Blah, blah.
Yeah, smart.
And then if
yeah,
blah,
and it's gonna work because if that's the first one is false, it's not gonna call the function. Yeah. Yes. Okay, now I see it. Nice.
Okay, so for word and yes.
Yeah, at the end of everything, that means the string is going to become empty, right?
Yes. So we check. We should check if our string is empty. Yeah, we can check it first. And if it is empty, what do we return?
Wait, why are we gonna check it first? Why not after?
That is the condition that should break the
recursion. The base. Oh yeah, we are inside the recursion now. So this is the base. Okay.
But what do we return?
True, because that means we found everything.
Yeah, exactly.
Good. So if not s, return true.
If not,
What's there now? Abby?
Wait, what's that forward in? Okay, wait. Okay, yeah, write it there then. So each time the s is true, we call recursion. Yeah, I believe so.
If s is empty, so if not s, then return true, right? Then loop through word dict. So for word and word dict, right? Compare the word with the beginning of s. How are we gonna do that?
I think Ningasi posts something like that. if s length of the word equal word is that
Yeah.
okay? That's very
There's
smart
also
slice.
starts with. There's also a string that starts with.
Yeah.
It checks if our. We can do either. I'll use the other one. So if s, and then we check only the first part. So if the first part, which is len word, so from 0 until len word, until the length of the index of the length of the word equals word, and we call the function with the rest of the string. That means we call self.word break with the rest of the string. So s from the len of word until the end of the string, right? And we give it the dictionary.
Wow.
Okay, and if these two are true, then it should return true. If it goes through all of that and it still doesn't find anything, it still doesn't return true, then it's obviously a false. All right?
What about the string empty check? Is the line
it's
3?
this one.
Oh yeah, because it's empty,
If
it's
not
gonna be
S or if.
okay.
Yeah.
Wow.
So this should work for these small ones. All right. Oh yeah.
What's that self.word break?
Self. Oh, this is the recursion, the recursive function. So this one calls.
Oh, okay.
Calls the function.
Would you need to
again
call self
with
on
the
it?
rest? Yes, it's this one. But with the rest of the string. So we said that we remove that, but we still have this one. We need to check if this is true also. If it is, then you return true. If it is not, then it goes through the next one. It's the same case where we have apple here and we check with app, right? You check with app, you find app, but you still need to know if the rest of the string also like checks out, if it also returns true. If it does not, we don't have any LE. This will return false, which will go back to this one. It will give us the string, and this one, it tells us this is not true. This is false. So it puts this back, and it loops through again, finds apple, and tries with apple also. So we don't go through the next one unless it is all of them is true. If it doesn't return true, then you abandon that combination and start with the next one. Make sense? Okay. So this one should work for small cases, right? The issue with this one, it does not pass the time limit.
Oh, takes so long.
Because it's if we have elements that repeat, it will go through all of the motions again. It will take too much time. Yeah, so for example, we have a lot of repeating elements. It will not work. So any solution as to how we can bypass this?
Could we try
where
tree as suggested?
Yeah, memoization. Pacman said memoization.
Oh, yes, that's true.
Wait, I did cut
Okay,
off. Someone said, what did you say? What the other person said? Someone did talk?
I was thinking guys he had suggested using a tree earlier.
Tree?
Yeah, there's also possible solution. But like, if can we like tweak this already algorithm, this one? I think Victor said memoization. So that's, I think that will work. So So like
That should work, yes. We have a dictionary that has, yes?
I just want like to say what is memoization. If someone like
Memoization is the process. Memoization is the process of keeping past like results. It's almost like caching. It's actually it's caching, where you keep previous responses or results, and you go through them and you check this cache before you run your function. So if for example I know that app exists in here, I don't have to like, or for example I have Apple phone and I have another Apple phone, right? If I go through again and I find Apple phone, Apple, I will not go again and check Apple first and then phone first and then Apple. It will like I will have this combination already in my inventory, already in my cache. I know this is true because I have phone, I have Apple, so I will return true before going through it again because I know I already went through it.
exist. So it's like saving it in a example hash table and just check before we launch another recursion. Check if that word exists.
So in this case, we can have a dictionary that has our string and it's whether it's true or false. So we can have like for example like this, and I know for example that app is false, right? So I will write it here. So if I go through app, I will save this false in my dictionary. I go through Apple, I go through phone, and here I find app again. Am I gonna check app again? No, I already have it in my list. I already know this doesn't work, right? So I will return false, so it can go straight to Apple and then phone.
I see. But in this case, it's gonna return true, right? Because app it exists.
In this example, yeah.
I mean, in the hash table, it's gonna have. I mean, in hash table, the app
should have Apple.
like app.
It will have Apple.
Like the app key is gonna have value true. Or
Apple, it will have true. Right? So it will first start with Apple. It will find it's true. And I also have phone Apple or Apple phone. And
wait,
it also is going to be true.
Apple have false?
App has false.
Yeah, why?
Apple has true.
Why app have false?
Why? Oh, because it's not gonna... Okay, I guess this is not the right way to do it.
Okay, yeah, it's kind of confusing. Because app is gonna be true in this case. Because it exists in the...
It will start with app. Okay, let's go through it. Since it is a recursion, we might need to start with the end. Okay, so let's go through phone. We have phone, right? Phone is true because it exists. It will return true. I'm starting with the end because the recursion logic, right? And then it will move on. So in a case where it goes through all of it, it finds phone, right? So it will return true on phone. Then it goes back and this. We have this, right? Apple phone. It will also be true because we have Apple and we have phone, right? But in a case where we have, for example, we tried app and we are left with LE phone, right? I am not gonna go through the rest trying to look for LE phone. I already know that this combination cannot be made by this. So let's just remove, we leave just Apple phone, right? I started with app, I removed app, I am left with LE phone. I know I'm gonna look for LE phone and I'm not gonna find it. This will return false. I am gonna write false here. So next time I find LE phone, I know directly that it's not possible with this combination. I don't have to look through it
Yeah,
all through our dictionary.
makes sense now. I think when we did go start from the end, it did make sense, because at the end you're gonna check Apple. It will match first.
Yes.
Perfect.
Okay. Any more questions?
Please, if you have question, don't be shy. Guess.
Okay. So, in this case, we can either have a function inside, right? And then we make our dictionary here, or can simply have an init here, right? That will make a self dot either memo or save, I guess save, and it makes the dictionary for us, so we don't have to, I guess, have another function that hosts this one. So in this case, we first, either first or after s, we check if s is in our self.save. So if we find it before we go into the loop, we check. For example, we have le phone, and we check if this is on our dictionary. We go through phone, it's true, and we find this, we return false immediately. If it was true, we return true immediately. We know that we have the words necessary to make up this combination. So if s in self.save, then you return self.save s. Right? You return the value that is attached to this string, right? Now, in our loop, if it is true, we know that this combination is true. It is like it is possible. Then we save it in our dictionary. So self.save s equals true. We save that this combination works.
I think we need else case here to save the false, right?
The false is going to be saved before the return. So self.save s equals false.
Oh.
So you save it before returning it.
Okay.
And this, I believe, should work. Yeah.
Oh,
yeah,
wait, can you submit it?
Okay. Yeah.
Nice.
There's also a small
Nice
little
work.
trick that is also very neat. A decorator called cache. Now,
Ooh.
I forget the yeah.
So we don't need
the
to.
name of it.
We don't need any like hash table or something. We can use the cache.
Yeah. It has its own caching system.
Wow.
Yeah, functools.
Sure.
So we have this. Okay, we don't have access to the actual dictionary, so I guess I'll just explain the logic. Say that we have a function that passes a and b as parameters, and it returns an integer c, for example, right? Now, if I decorate this function with cache, every time this function returns c, it will save it in its memory as this format. Both the parameters would be a tuple as key, right? And the return would be the value, right? So even if we have we have, for example, D, E, right? The dictionary would have all of these as a tuple, and then the value would be C. And if I keep calling this and changing this, changing these like parameters, for example, I will have, again, I will say G and F and, I don't know, T, and it will return another value, for example, R. It will keep having these, this dictionary will keep having these key and values. Next time I call with this, it will return automatically this. So this is like
Wow.
automatic caching. It takes care of the caching for us. Now, the issue with this in
Like
our
read
case
this.
is, the issue with this in our case is this list, because if I attempt to make a dictionary with a list as a key, it will tell me that it's not hashable. So if in this case I remove this save, right? I remove, the error that I would get is that word dict is not hashable. Type list, which is word param2, is not hashable. There are a couple ways we can take care of this, right? That would also involve making another function. We would have two functions. The first way, I guess, would be to have this call another function. So can have this as a helper, right? And it will only it will have s and word dict, but in here, when we call word break, I will turn this list into a tuple. So I will call self helper with the same string, but a tuple of word dict, right? So I am, instead of caching word break, I am caching the helper.
Genius.
Right? The helper would receive s. It will receive the word dict as a tuple, because if I do the same thing here, but I instead give it a tuple,
It will.
no. Yes, it will work. An array would not work, but a tuple does.
Okay.
So here we just change the type of the word dict. It is still used the same way, but this time. Oh, right. Oh boy.
Maybe something. Maybe some intuition or something.
Oh yeah.
Return.
I'm still calling word break. I need to call the function itself, helper.
Still something there. We're gonna return self-helper.
Yeah, I think so.
Like line 3.
Oh boy. Yeah, obviously.
Ooh, nice.
And it passes the one that is
nice.
The long one.
Wait, I have a test to do. I don't think it's gonna work, but it's gonna be fun. Like, what if we change the line 2? The line 2, we add tuple inside word dict.
It doesn't work. It doesn't work. You can't change the parameter.
Okay.
You can't change it.
Okay.
Like here, tuple?
Like.
Or.
Maybe. Like I'm not sure. Maybe
no,
like
it won't work.
It will? No. Okay.
No.
Nice. Good job.
I'm pretty sure it won't. Yeah, or you can put this. Yeah, you can't. Invalid syntax. Or I guess you can leave the cache on word break and put this inside. So this helper inside the function, we don't even need to pass word dict. And it will keep only s as the parameter. Word dict. And you put this at the end. And you don't even pass word dict, but it has access to word dict since it is inside of the function. Right? Makes sense? And you cache this. Oh, no, you don't cache this. Nice. You cache the helper, but you don't pass the word dict. So the cache will only have s as the parameter. It will be like this, s, and then the bool. And different s's would have different, and this would be closer to what our own dictionary was when we did it manually. Make sense?
Nice. Nice.
And it will not be self. And it would not be self. And it would not take self.
I usually do this because I don't need to write self.
Yeah.
And also kinda more cleaner. Nice.
All of these are fast. Yeah. That's it. That is it, that is all. I wanna close it.
Yeah, that's it. I was just writing in chat. Someone, Hazel, I was asking like if there is a cache system in NC. I did some research. I don't think there is like a built-in, but you can like do something like this, where you implement caching. So that was it. Thank you everyone for joining, and thank you, Sabah, so much. This was so fun, and you are very like awesome at like presenting, explaining, solution brainstorming. Yeah, you're really fun to like watch. And
sorry, Musi, before you
yes,
before
brother.
you wrap this up, I know that I've come late, so if you
Yes.
if there by any chance you can provide just a quick wrap up.
Yeah.
Recap.
Yeah. So what's
the last challenge?
Yeah. Okay, you wanna go ahead, give him an idea of like problem and how we did solve it? Just like 10 second or 20 second.
Okay. So basically we have s is a string, we have word dict is words. We check if these words can in any combination get to s, right? So we check if our string is empty, right? If it is, then we return true. And then we check each word in our word dictionary, and if that word exists in the beginning of so if, for example, apple, if it exists in the beginning of our string, then we cut it out of the string and call the recursive function again on the rest of the string, right? And then we check if any of our dictionary words exist in the beginning of the next string, and go on until either the string is empty, which means that it is true, right? We can change all of these, or we can come up with a combination that ends in our string, or it returns false, which means that no combination will ever make up our string. Yeah, and we used a caching system to make it faster.
I'm sure you can like just watch the recording of this session. I'm gonna post like in 1 hour. It's like a really fun session, and we learn a lot. Backtracking and the caching system. And the first problem I think we solved it with the algorithm called Dutch flag, which is really cool. That's it. So next week, so this was week 9, I believe. So next week gonna be left week 10, and we only have 3 weeks left, which is amazing. So if we finish this 3 week, we finish 3 months. That is gonna be like 48 PLD, which is crazy. We learned so much, and if someone want like prepare some of these LeetCodes that are coming, you can just check them out. If something you're comfortable with, just hit me up, say that you wanna like show this or present this, and yeah, the stage is yours. Have a good night, and thank you everyone.
Thank you.